Okay, so part two of this lecture is you want to find the Green's functions for the potentials V and A in the non-static case. So we can title this Green's functions. Okay, so first, before we go ahead and find the Green's function, I should probably explain what a Green's function is. So the idea is, let's consider a differential equation. So consider a differential equation, and we'll just write kind of a generic differential equation, D acting on V of R, and then this will be equal to some function f of R. Okay, so it stands for just, the D is just some differential equation, and we should solve it for V. Okay, and we'll work an example in a second if that seems a little abstract. Anyways, so the Green's function for D satisfies D acting on our Green's function of R minus R prime is equal to delta cubed of R minus R prime, where delta cube is the three-dimensional Dirac delta function. Okay, so the Green's function is specific to a particular differential operator, and it's just the one that gives you your f of R being equal to the delta function. Okay, so before we do an example, let's first answer the question, why is the Green's function useful? Okay, so our claim is that for the differential equation dv of R equals delta q, is equal to f of R. Getting ahead of myself. So the same differential equation we had before, dv of R is equal to some function of R. Then the solution is v of R equals the integral over R prime, d cubed R prime, g of R minus R prime, f of R prime. Okay. So that's going to be our solution to the differential equation. Okay, so the idea is we just need to solve the differential equation once to get the Green's function, and once we have that, we can get v of R for any generic f of R just by doing this integral here. Okay, so let's prove this. Prove. Okay. Also, just acts with a differential operator, D acting on V of R is equal to the integral d cubed R prime of D acting on our Green's function, G of R minus R prime, f of R prime. Now, kind of important here is the fact that our derivative operator D only acts on R and not R prime. Okay, you notice there are no R primes on the left-hand side. Okay, so the only thing on the right-hand side that the derivative operator acts on is our Green's function G. It doesn't affect f of R prime. It doesn't affect the integral at all. So what we have then is that dv of R is equal to the integral d cubed R prime. The derivative operator acting on our Green's function gives us delta cubed of R minus R prime times f of R prime. Okay, and then when we do the delta function integral, that just gives us d acting on v of R gives us f of R, which is what we wanted it to be. Okay, so that's what the Green's function does. It gives us a nice easy way to solve our differential equations for generic f of r on the right hand side. Okay, so let's do an example from electrostatics. So we want to find the Green's function for V. Okay, so in electrostatics we have the equation del squared V of R equals minus rho on epsilon naught. Okay, so the Green's function, find the Green's function, is just del squared acting on G of R minus R prime is equal to the delta function, delta cubed of R minus R prime. Okay. So get rid of that. Okay. So believe it or not, we actually already know the answer to this. You saw this last semester, so I'll just put recall that del squared of 1 on R is equal to minus 4 pi delta function of R. Okay, and remember this is the script R, so R is just shorthand for R minus R prime. Okay, I'm not going to rederive that here, but we can kind of justify that last step. So let's write this as an aside. Kind of a way of remembering this is we know that del squared V is equal to minus rho on epsilon naught. That just comes from Gauss's law. Del dot E is rho on epsilon naught, and then V is minus grad V is equal to E. Well, so if we plug in for a point source of unit charge, well, the potential for a point source of unit charge is 1 over 4 pi epsilon naught R, and then the point source, that just gives us minus 1 on epsilon naught, point charge del cubed of R minus R prime. Or I guess I could have just written that as R. So the point is, if we just multiply by 1 over 4 pi epsilon naught, then del squared 1 on R is equal to minus 4 pi three-dimensional Dirac delta function of, and I'll use the shorthand of script R there for R minus R prime. Okay, so that's just kind of an easy way of remembering that, because you know that del squared V is minus rho and epsilon naught, and you remember hopefully the potential for a point charge. Okay, anyways, so we can just let, so again we're, I guess, rewrite this here. So we have del squared G using the shorthand of R is equal to delta cubed of R, and del squared of 1 on R is equal to minus 4 pi delta cubed of R. So putting those two together, G of R is equal to minus 1 on 4 pi R. Okay, so we have that. And so the nice thing about this is now, for any generic charge distribution, we have V of R is equal to the integral d cubed R prime times the Green's function minus 1 on 4 pi R times our f of R, which is minus rho of R prime on epsilon naught. Okay, so this is our Green's function, and this is our f of R. F of R prime there. So just clean that up a little bit. we have v of r is equal to the integral d cubed r prime rho of r prime on 4 pi epsilon naught r. So this kind of gives us some physical intuition of what the Green's function is. What we're basically saying is the Green's function is the solution with a point source, with a delta function source. So really what we're saying is that the potential with an extended source, with a generic source, all we need to do is we just add up all the point sources. And so as an integral that you've seen before, we're just integrating with the charge distribution and treating like a bunch of point sources and adding them all up. So that's really all there is to the Green's function.